All right, good morning, afternoon again, or whatever it is. We're kind of done with the mechanical aspects of the heart for now. We've kind of gone through the valves, looked at the left and right heart, that is the systemic and the pulmonary circuit, kind of looked at the blood flow through, look at some of the pressure differences, that sort of thing. What we're going to look at next will be the electrical characteristics of the heart. Now, we already actually went over a little bit of this. Remember, if you're looking at cardiac muscle cells, at the cell-to-cell junction, we remember from anatomy 1, and we've also discussed it in 2, there are gap junctions. These allow the cells, all the cells in the heart are connected with these gap junctions. So it's kind of acting like one giant cell. That is, information, ions, action potentials, what have you, can move from cell to cell through these gap junctions. So it's kind of working like one gigantic cell, not a bunch of individual cells, which is what you want. You know, the heart, all cells have to contract at once to squeeze on that blood. We also, I think, looked at the autorhythmicity or the myogenicity of the heart. That is, it can generate its own action potential, unlike skeletal muscles. And it does that by using those sodium leak channels. Sodium flows in, eventually reach threshold, cell generates an action potential. Again, many of the cells in the heart can generate their own action potential, but they all do it at different frequencies or different rates. But because of the gap junctions, whichever cell in the heart generates action potentials the fastest, that's the pacemaker. Now, what we look at next, inside the heart, there are a number of modified cardiac muscle cells, or cardiomyocytes, they'll sometimes be called in your text. Many of these cells, these cardiac muscle cells, well, they are muscle cells. They're modified basically to generate and conduct an action potential, an impulse through the heart. So they're kind of working a little bit like a nerve cell. They're muscle cells, but some of them don't even contract anymore. So what we're going to do is look at how the electrical signal passes through the heart. And anytime you're looking at, the electrical characteristics of the heart, kind of refer back to, how the heart is working mechanically, because that's what's important. Any electrical changes that interfere or affect how the heart's going to pump are going to affect cardiac output and will be detrimental for efficiency. So what we're going to do first is look at sort of the normal pathway of the electrical signal through the heart. So we'll look at the direction it moves, and also look at a few time intervals. Some of these intervals have to be the time it takes for the impulse to get from one point to another can impact how the heart works. So first I'll scribble it on here, then I'll patch in a little video with a nicer picture. But we can imagine the heart looks something like this. There's I won't draw on the valves, but that's your right atria, right ventricle, left atria, left ventricle. I won't put in the valves and stuff at this point. But what you'd find is in the wall of the right atria, kind of close to where the superior vena cava comes in, there's a little knot or clump of cells. This little clump of cells is usually referred to, we'll just use the abbreviation, SA node. SA is for sinoatrial node. I'm just going to put SA node down on the board. And the important characteristics of these cells is in a normal heart, the cells of the SA node tend to have the fastest sort of intrinsic rhythm. That means the cells of the SA node are normally the pacemaker of the heart. Remember, the fastest cell is going to pace the heart. The SA node contains the fastest cells. It's the pacemaker. Now, what I'm going to do for time events, t equals 0 seconds. That's when the impulse first originates in these cells in the SA node. Now, these impulses will move through tracts. Again, these are just collections of cardiac muscle cells that act to conduct the impulse throughout the atria. So the SA node fires, and these pathways conduct that impulse through the atria very rapidly. Now, I lied to you a little bit earlier. Remember, I said, well, I didn't really lie. All the cells in the heart are connected with gap junctions. That's true, but it turns out there's a big disc of cartilage, connective tissue, I should say, not just cartilage, between the atria and the ventricles. So it is connective tissue. It's part of what they call the cardiac skeleton. It kind of acts as a site where the valves can be anchored in place, that sort of thing. But the problem with connective tissue, it does not conduct action potentials. It's mostly extracellular matrix. So what that means is, if this impulse travels this way and it tries to go down to the ventricles, it stopped right there. This impulse moving down this pathway goes here, it stopped right there. This is almost like an insulating rubber disc, like it won't let the impulses through. There's only one spot where the atria and ventricles are connected. It's right along the interventricular intraatrial septum, right here. There is another specialized clump of cells. I'll make another circle. This group of cells is called the AV node. It's just an abbreviation for atrioventricular node, because it's kind of right there at the junction between the atria and the ventricles, right at the septum. Now, for timing, if we watch this impulse move, to go from the SA node to kind of the farthest reaches of the atria, that takes around 0.09 seconds. To go from the SA node to this AV node, that time about 0.06 seconds. So 0.06 of a second after the SA node fires, the impulse makes its way to the AV node. So I could draw something like this. I'll just isolate the nodes. That's your SA node. Here's your AV node. So to go from the SA node to the AV node, it's about 0.06 seconds. Now, here's what's kind of weird. Once that impulse reaches the AV node, it takes it another 1/10 of a second, 0.10 of a second, to wind its way through these cells of the AV node. Small diameter cells, really low conduction velocity, which means by the time the impulse exits the AV node, it's been 0.16 of a second. So the SA node fires and the impulse sweeps through the atria, but then the impulse gets delayed or held up in that AV node for another 1/10 of a second. So it's going to be 0.16 seconds before that impulse makes it to the ventricles. This is weird. Why is it that slow? All right, you might think, well, it's just some evolutionary remnants, an efficient leftover from a fish heart or something. No. Remember what's happening mechanically. When the heart contracts, which part contracts first? The atria. If the atria and ventricles contracted at the same time, the atria are wimpy. They don't have much muscle. Ventricles are massive. If they contract at the same time, those AV valves are immediately slamming shut. You're not going to get that 20% sort of top off that you need from the atria. So the delay here is mechanically important. What's happening electrically, the impulse is moving through the AV node, but mechanically, the atria have already depolarized. They're squeezing on the blood, and this is when you're topping off the ventricles. Then, after the impulse leaves the AV node, it will travel down a bundle of conducting fibers running right down the interventricular septum. This bundle of conducting fibers is called, you can either call it the AV, or atrioventricular bundle, or it's called the bundle of HIS. AV bundle is more descriptive. That's what I'll typically use. And the impulse travels rapidly down the AV bundle. Then it's going to split into two parts. We call these left and right bundle branches, which will move towards the apex of the heart. Then once they reach the apex, they just move up and they split and they wrap around from the apex to the base, wrap around the front of the heart, the back of the heart. All these smaller fibers, they're just called Purkinje fibers. That's the pathway. So SA node through the atria to the AV node, delayed a 1/10 of a second, then through the AV bundle, left and right bundle branches, and then spread out around the heart into Purkinje fibers. It's pretty fast. Once the impulse reaches the ventricle here in the AV node, it only takes it's about 0.06 seconds to sweep through the rest of the heart. So you're talking the impulse starts here and sweeps through the ventricles, the whole heart, in about 0.22 seconds or so. That is the normal pathway of the electrical signal through the heart. We'll stop there for this one, and I'll put some other stuff up in just a minute. All right, here's a somewhat prettier picture than the one I had on my screen, but see this yellow mass here? This is a right atria. There's your superior vena cava. That's the sinoatrial node or SA node right there. That's what originates the impulse. That's the pacemaker, and the impulse will sweep through the atria. This little yellow mass are indicating right here, that's the AV node. That'll receive the impulse, delays it for about 1/10 of a second. Then it will go through the AV bundle, or bundle of His, split into right and left bundle branches, move to the apex, and then splits into all these Purkinje fibers that carry the impulse throughout the heart. So that's the normal pathway and some of the timing for this impulse to sweep through the atria and the ventricles. And of course, keep in mind, this impulse, as the heart depolarizes, like other muscles, when you depolarize a muscle cell, that's when it's going to begin to contract. So the impulse sweeps through the atria first, they contract, delayed here 1/10 of a second, so the atria is still contracting. Then the impulse moves rapidly through the ventricles, and they contract and force out the blood. And that'll do it for the normal pathway of the electrical signal through the heart.